In this lecture, we are going to discuss about the gas turbine engine and its applications. The gas turbine is an internal combustion engine that uses air as the working fluid. The engine extracts chemical energy from the fuel and converts it to mechanical energy using the gaseous energy of the working fluid to drive the engine. The efficiency of a gas turbine engine is lower than both SI and diesel engines. However, due to its excellent power to weight ratio, its application is limitless because it can be fitted in a very small space and can produce enormous amount of power. In a reciprocating internal combustion engine, the functions of the intake, compression, combustion and exhaust all take place in the same combustion chamber. Hence, each stage must have its own place in the chamber during its respective part of the combustion cycle. But in a gas turbine engine, there are separate sections which are devoted for each function, and all functions are performed simultaneously without any interruption. These sections are air inlet, compressor section, combustion chamber, turbine section, and exhaust section. There are various types of gas turbine engines. There are turbojets, turbofan, turboprop, and turboshafts. These type of gas turbine engines are used to give power to aeroplanes, helicopters, ships, trains, electrical generators and power plants, pumps, gas compressors, tanks, and its applications are limitless. In the next lecture, we are going to discuss the power generation mechanism inside the gas turbine engine. In this lecture, we are going to study the power generation mechanism inside a gas turbine engine. You can see here, this is a cutout of the gas turbine engine. This is a type of the gas turbine engine, and you can see there are various stages through which the air flows and the power gets generated. You can see here, these are the various stages: the intake, the compression, combustion and exhaust. And these are the various segments: air inlet, compression, combustion chamber, turbine and exhaust. This is the cold section where the temperature is less, and this is the hot section where the temperature increases drastically. Here basically what happens is, the air, which is the working fluid, gets sucked in due to the compressor, and it gets compressed, and then it flows into the combustion chamber where the fuel is injected and mixed with the air, and then it ignites to produce very high pressures, and that in turn rotates the turbine. A portion of this energy that is getting generated inside the combustion chamber gets consumed by this turbine section, which rotates to rotate this shaft and in turn rotate this entire compression section, which again sucks the air and flows it through the combustion chamber. The part of energy is consumed by turbine section and the other part is transferred to the exhaust, which produces the thrust to drive the aircraft. This distribution of power depends upon the application of the engine. In helicopters, the energy which is diverted to thrust is very less as compared to the energy which is utilized in the turbine. You can find various resources which will guide you exactly how the power gets generated inside the gas turbine engine. But our interest in this course is, we should know the importance of blades in this power generation mechanism. In the next video, we are going to see the importance of blades during this power generation mechanism and in the gas turbine engine. As we have seen from the previous lecture, the power generation in a gas turbine engine only depends upon the amount of air it can suck from the atmosphere and then how efficiently the air flows through the engine to finally get utilized in the turbine and the exhaust sections. All this depends only on the thousands of blades that are used inside the gas turbine engine in the compressor section and the turbine section and are solely responsible for intake and smooth flow of air inside the engine. Blades are the most abused part in the gas turbine engine and hence are prone to failures very easily, and so its design is the most vital part of the success of any gas turbine engine's design and operation. Blades are used in various forms: compressor blades, turbine blades, guide vanes which are the stator vanes, and impellers which are axial compressors. You can see here, these are the blades. These are the various stages of blade. Each set of blade is a stage of blade. So here there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 stages of compressor blades. And here we have 1, 2, 3 stages of turbine blade. If you see the engine cutout, you can see there are various types of blades with various geometries. In this course, we will discuss series of projects and we are going to study real industrial drawings of each variety of blade and then convert them into 3D model. Here if you see, this is the compressor section where the entire work of this compressor section is to suck the air from the atmosphere and compress it and send it to the combustion chamber where it expands and then flows to the turbine section, which is this. These are each a set of blades defining a single stage of blade. You can see this is a stage of blade, this is a stage of blade. These are individual stages of blades. This is a compressor stage of blade. And here, this is the turbine stage of blade. In the next lecture, we are going to start with the basics of aerofoil. We are going to know about the geometries, and then in the first project, we are going to learn how to create the aerofoils. Before you generate any blade drawing, you should understand that any blade drawing will constitute aerofoils. So, we should first understand aerofoils and then we can go for making the blade model and understand the blade drawing. In this section, we are going to discuss about the aerofoils. We are going to introduce ourselves to the aerofoils and then in the next sections, we are going to learn the aerofoils in details. Drag is the resistance to airflow. A flat surface produces 100% drag. A spinning circular surface produces 50% drag. An aerofoil is a geometry which produces only 5 to 15% drag. Hence, aerofoils are used widely in applications requiring low drag to airflow, like gas turbine engine and aircraft wings. The concept of aerofoils or the airfoil has been developed from the birds, which use these geometries for gaining maximum lift at minimum drag while flying. We are not going to discuss in details about the aerofoil theory, which is enormous and which you can find in any book, but we are going to discuss the application part of it. there are many types of aerofoils. You can see here, these are the types of aerofoils, various types of aerofoils that you can find. In gas turbine engine, the main body of the blade through which the fluid flow occurs is composed of a set of aerofoils which are stacked and related to the engine axis. You can see here, this is the main body of the aerofoil, and these are the various sections containing the aerofoils. So, if we want to design and develop a blade, we must be thorough with the aerofoil design and its geometry. In the next lecture, we are going to discuss about the aerofoil geometry, which is used in the industrial blade design drawings. In this lecture, we are going to know about the various terms that we use for defining an aerofoil and in context with the aerofoil. Here, we have some basic terms that we use. You can see in this drawing here, this blue indicates a aerofoil. This is a aerofoil structure. In the aerofoil, this surface is called the upper or the concave side, and this surface is called the lower or the convex side. Here, this portion is called the leading edge. This side the air enters the engine, and this is the trailing edge. This side the air flows out of this blade or the aerofoil profile. The tangential length between the leading edge and the trailing edge. I am saying tangential length because this leading edge consists of an arc, which is a part of a circle, and the trailing edge also consists of an arc, which is a part of a circle. So, the tangential distance between these two circles is the chord. Now, there is one more term that we need to understand. There are many type of explanations for camber, but this is the most easiest explanation, and you can develop this camber very easily by using this method. You can see, this is the aerofoil. The blue indicates the aerofoil. These circles I have created by taking tangency between this upper convex side and this lower concave side, which defines this local thickness. So this circle defines the local thickness between the convex and the concave side at this position. Similarly, each circle defines its local thickness at that particular position in the aerofoil. Here you can see this is Cmax, or the maximum thickness of the aerofoil. It will be at a particular point. So this thickness we have to develop for many positions. There is no such definition of a position. You can do it anywhere. The maximum number of circles, the better. So what you have to do is, you have to connect the center of these circles which you have created through spline. You can see this is a spline which contains the center of the circles. This spline is the camber. So at any point of time, if you want to generate a camber, this is the best way to do it. Now let us learn something more which is related to the actual blade drawing. In the actual blade drawing, the nomenclature of the aerofoil will be given something like this. Here, this x-axis and the y-axis are the axes which are related to the engine and the blade root. It is this axis, which is the x-axis and y-axis, about which the coordinates of the aerofoil will be defined. If you see here, this is the main drawing. In this drawing, you will get this table of aerofoil data. In any type of blade drawing, you will get this data, because without this data, you cannot generate an aerofoil. Now, here you can see there is X value, Y value, and there will be a Z value somewhere. You can see this is the section heights. We will know the details about this drawing. You need not worry, because this is the first project that we will be handling. I just need to explain this table of aerofoil data to you. Here you can see there are X and Y values. There are various sections. You need not bother about that. This is the X and Y values. These X and Y values have been generated by using this X-axis and Y-axis as the reference. Here, as I have already told you, this is the chord, this is the leading edge radius, this is the trailing edge radius, this is the distance between the leading edge and the Y-axis. Similarly, this XTE is the distance between the trailing edge and the Y-axis. This is the maximum thickness, which I have already told you. Now, there is a very important dimension which is a part of the inspection process that you will be encountering in real production situations, which is this thickness. Here you can see at 3 mm distance, this 3 is not fixed. It depends upon the designer how much he is going to give, but in our drawings we have used 3, and at this distance of 3 from the leading edge, we have a thickness of the blade. This thickness is called the leading edge thickness. Similarly, we have a trailing edge thickness here. At 3 mm from the trailing edge, there is a thickness of the blade which is called the trailing edge thickness. So, if you see the table, in table we have all these values. We have the chord, we have the Cmax, the leading edge radius, the leading edge thickness, trailing edge radius, trailing edge thickness, and XLE, XTE. These parameters may or may not be required for drawing the aerofoil of the blade, but these parameters are mandatory for inspection of the blade so that it can be fitted onto the engine. Because practically, if you see, if you have a physical blade, you have to check it, you have to inspect it. So for inspection, these parameters are vital. So for now, this is all about the aerofoil. In the next lecture, we are going to see how to draw aerofoil from the given data. And in the further sections, you are going to be very clear about aerofoil and the blade geometries. The data of the aerofoil in the drawing will be given in the format of a table. You can see in this drawing, here this is a table which contains the aerofoil data. Already we have seen these are the various parameters which define an aerofoil. And here in this table, there are various coordinates which will define the points of the aerofoil. Here, these are the parameters. The most important parameters are, of course, the coordinates and the chord, leading edge radius, trailing edge radius, because these are required for making the aerofoil inside the 3D modeling software package. This is the table you will get in most of the drawings which define the aerofoils used in the blades. This table contains all the parameters associated with the aerofoils as defined by the designer. A designer may represent an aerofoil by using two methods. The first method is a single series of points. When connected, it will define the concave side, convex side, leading side and trailing side at once. And the second method is one set of coordinates which will define the convex side and other series defining the concave side. The leading and the trailing edges will be defined by the arc radius. In case the designer has opted for the first method, then there is no problem for us. We just need to import the data and our aerofoil will be ready, which has been shown and used in the 5th project of an impeller in this course. But in case the designer has selected the second method, then there are 4 cases that will arise while developing the leading and trailing edges of the aerofoil. Of course, you will first import the aerofoil data and you will generate the concave and the convex side, but you have to close it by using the leading and trailing circles or the arcs. The first case is the ideal condition. You can see here, this is the ideal condition. By ideal, I mean I just need to create the arcs which contain the endpoints of these splines and I'll give the radius, automatically the tangential constraint will be created. Or let us generate and we will see. I have taken an arc and I'll connect this endpoint and I'll give a second point and I'll connect third point here. Let me give the tangency between this arc and this spline. I'll give tangency. Click on OK. The arc is constrained. Now let us give the radius. You can see the radius. The radius is 0.75. You can see here, this is the aerofoil data of the aerofoil that we have generated here. And in this aerofoil data, if you move over to this row, you can see the leading edge radius is 0.75. You can see here the radius is 0.75. So the aerofoil coordinates are exactly positioned to match the endpoints of the leading and trailing arcs. So while drawing the arcs, taking the endpoints, the perfect leading and trailing edges will be automatically developed. So if the designer chooses this method, we have absolutely no problems. But this is the ideal condition, which about 90% of the chances this won't be the case. The case 2 is for longer profile data. Here the coordinates may be overflowing and passes the leading and trailing circles. If you see here, you cannot identify here, but if you see the trailing side, you can see how sharp this is. So if you form an arc, it will form somewhere here. So this data is actually the overflowing data. So in this case, we will not get a perfect arc if we connect the endpoints of the leading or the trailing end points of concave and convex side. We need to trim the extra portions of the spline or profile so that a completely closed aerofoil loop can be obtained. So we have to decide which parameter we have to control while modeling so that the procedure can be adapted accordingly. If we want to control the leading and trailing edge radius, then we can do something like this. Suppose let us take this trailing side and let us develop this arc and let us give a radius. As I have already told you, if you want to control the leading and trailing radius, then you have to give this value. And if you see the data here, you can see the trailing edge radius is 0.25. Let us give that. Double click here and we will give 0.25. You can see a perfect trailing edge radius has been generated. Now we just have to use trimming and we have to trim these extra portions. You can see. So this is how you will control a aerofoil if you have overflowing data. Now let us move over to the leading side. And here also we will do the same thing. Instead of arc, you can also take a circle, and we will take tangency between these two. Again, a tangency between these two. Now we just need to give the radius. Here we will take the radius as you can see the trailing edge radius is 0.75. We will give a value here 0.75. You can see the circle is completely constrained. Now we will take trimming. This trim is available in every software, and what I am doing here in CATIA is same in any software. So you need not feel that I am doing it in CATIA and I am not doing it in Siemens NX or Fusion 360 or any other software, because the details of this drawing process will be discussed in each and every project. So you need not worry about that. Here I just want you to understand the process of generating an aerofoil. So if you have overflowing data, that is, if you have more number of points defining the aerofoils, then you can trim the edges to get the aerofoil leading and trailing edges something like this. And if you want to control it by giving the radius, you can give the radius. Suppose instead of this radius, you want to control it by giving the distribution of the edge distances. You can see these are the distribution, leading edge and the trailing edge distribution. If you want to give these two and if you want to constrain it, then you can do it. You just have to delete this radius. You can see I can delete this radius, select and delete, and even I can also select this and delete, and I have to give the distances. I'll take this circle and this axis, which is the y-axis, and this distance I can give XLE. Let us check. You can see XLE value is 14.975. Let us give that 14.975. You can see it is constrained. So you can constrain the leading and trailing circles or the arcs by giving various parameters. Leading edge radius and the trailing edge radius. The second set of parameters may be distribution, which is XLE and XTE about the y-axis, or maybe you can go for leading edge radius and the chord. So there are various techniques that you can use for actually constraining the aerofoil. These techniques has to be selected which suit to our need in the industry. But one thing has to be perfect. The tangency should always be maintained in the transition or the joints. Like if you see here, you do whatever you want, but the tangency between the transitions must be maintained. There is also a case if you have a shorter profile. You can see in this drawing, I have a shorter profile. If you generate a circle, then only you can see. Let us generate a circle here. We'll create a circle and we will give it a radius. The radius value, you can see we have 0.75 here, leading edge radius. So let us give here 0.75. Now, if I move this circle, you can see this circle doesn't satisfy both the splines. So what we have to do here is, we have to create tangential lines. I'll take this point and generate a line something like this, and again I'll take a line. At this point, I'll generate a line something like this. Now I'll take this line and this spline and create a tangency relation between them. Again this line and this spline, and create a tangency relation. Now you can see this entire thing is tangent. So what I will do is I will take tangency between this circle and this line. Again, tangency between this circle and this line. You can see the circle is completely constrained. Now I'll take trimming and trim these portions which are not required. Now you can see the circle has been constrained and the leading edge has been generated. So this is how you can generate the aerofoil if you are short of the coordinate values. Here also we have to decide which parameter you have to control: the radius, the chord, the distribution, like I have said in the earlier case. Accordingly, you can constrain this arc. There may be cases where there are mixed profile data. That is, one side there may be more data and one side there will be less data. With data I mean the coordinates of the points of the aerofoil. You can see in this aerofoil there is a mixed data. You can see here this is longer and this is short. If you go to the trailing side, you will see better. You can see this is very long, that is overflowing data, and this only ends till here. So if you want to generate a leading and trailing edge, in this case we can go for circle. You can see, and let us give the radius which is 0.75. Now if you move this, you can see you can create a tangency with the convex side, but you cannot create tangency with this concave side. So I'll take line, connect this point, generate a line something like this, and we will take tangency between these two. Now I'll take the circle and create a tangency with this line. Similarly, I'll take this spline and this circle and create a tangency. Now you can see that the circle is completely constrained. We will take trimming and trim the unnecessary portions. If you zoom in, you can see this is the overflowing data. We will trim this, and you can see the edge is generated. So I have shown you 4 cases. Accordingly, you have to decide how to generate the aerofoil's leading and trailing edges. All these cases we will be seeing in the aerofoils that we developed in the projects, which are the 5 projects that you are going to encounter in this course. So let's start the projects and we will get to know more about these aerofoils. With the knowledge that you have gained in this video, you will be able to easily start the aerofoil drawing process while generating the 3D models. In the next section, we are going to start the very first project of this course, which is 5th stage compressor blade of a gas turbine engine. In this section, we are going to start with the first project, which is 5th stage compressor rotor blade of an aero engine. This is the blade that we are going to create in this section and project 1. This contains an axial root and of course we have the profiles. Let us see the drawing by using which we are going to create the 3D model. You can see this is the drawing. This blade contains 5 sections at different heights. These heights are the Z values and the X and Y coordinates are given here in this table. This table contains all the profile data, the X and Y. You can see this is section 1, 2, 3, 4 and 5. For the 5 sections, we have 5 set of data. YCC stands for concave, YCV stands for convex. So we have concave and convex data of the aerofoil here in this table. Here we have the chord, Cmax, leading edge radius, trailing edge radius, and the leading edge thickness, trailing edge thickness, and XLE and XTE. We have discussed about this aerofoil in the previous section. You can see this is the dovetail route, and this dovetail route, if you see here, this line, along this line we have developed a section which is AA, and this is the view. From this view we have taken this detail view and we have gone for 2:1 scaling of the view, and all the dimensions have been specified here. This is the dovetail route. So in the next video we are going to start working on the aerofoils, and then in the further videos we will create those aerofoils and we will move on to create the axial dovetail route. In this lecture we are going to prepare the aerofoil data that has been given in the drawing. Here in the drawing you can see this is the table of aerofoil data that has been given with respect to the aerofoils in these 5 sections. The first work that you have to do is, if you have got a paper printout of this drawing, then you have to type this drawing into Excel, which I have it here. So this entire thing has to be typed and made ready in Excel. You can see these are the coordinates. This is not required. You have to type all these coordinates and you have to arrange it according to X, Y and Z. Like this is section 1, and from this section 1 data you have X, Y and Z is the section height. Section height we can get it from here. The section 1 is 15 mm from the base. So if you are keeping your coordinate system at the base, then you have to specify a Z value of 15. Now this entire thing you have to convert into X, Y and Z. I have already done it. You can see here this is modified to accumulate X and Z value in all the section concave and convex data. If you see here, only a single X is given, and with a single X value, what is the variation of Y that has been given? So this is the format that you will encounter in any type of blade drawing. Well, of course the designer has his own ways, but this is a standard format because you cannot go around and print numerous data into the drawing sheet. You have to give maximum information in little bit of space. That's why designers follow this technique, where we need not give X and Z, and the area consumed by this table will also be very less. Now, if you see here, for first section, this is the concave and this is the convex. So the coordinate will be X, Y, CC and Z. Then for CV, X, Y, CV and Z. So that is the format that you should follow in this Excel sheet. Now you can see here for the first section we are having the concave coordinates X, Y, CC and Z. Similarly X, Y, CV and Z. And for second section X, Y, CC, Z. X, Y, CV and Z. So these are the various coordinates of the sections. Now we have to use these coordinates and feed into our CATIA importing file, which is a macro. It's an Excel macro file. So this is how you should arrange the coordinates so that we can use it further. This file I'll share it with you so that you need not type and make it again, but I suggest you should make it again so that you will have the practice. In the next video, we are going to import the coordinate file into CATIA for creating the aerofoils. In the last lecture, we had created this Excel file. But this Excel file we cannot import into CATIA. We have to convert it into an Excel macro file, which is by default given in CATIA. You have to find it out from the CATIA installation directory. Let us open my computer or this PC, and here we should browse to the CATIA installation folder. I have my CATIA installation folder somewhere here. In C drive, program files and Dassault systems. You have to find this folder. In B20, Intel A and code, you have this command. Double click on command. When you move over down, you will find Excel files. You can see GSD point spline loft from Excel. This is the Excel macro file, which is used for importing the point file into CATIA. So we will copy this, right click and copy, and we can paste it in our required location. Let us paste in this exercise folder. Right click and paste. When I double click and open this, you can see if your macros are disabled, then you have to enable it for this file to operate. Here I'll enable the content, but if you want to do it, you go to File, Options, and in this Options, Excel Options panel, go to Trust Center. Here, go to Trust Center Settings, and in this, you have to click on Macro Settings. Here, we have to click on Enable All Macros so that our macro file can run. Click on OK and OK again. So, the macro has been enabled. Now, let us see the file. Here we have some commands. Start loft and here start curve. These are the coordinates, the X, Y and Z values. Here in between the start curve and end curve, whatever you give, that will form a single curve, or it will import the points and connect them through splines, through a single spline. Similarly, suppose we are having 4 sections or 5 sections, we have to create 5 set of start curve and end curves. When you see the drawing, here we have 5 sections. And all these 5 sections have their individual X, Y, Z. Now, in this file that we have created, we have already arranged it. We just need to copy this. You can see, I can copy here, right click and copy, and then we will paste it here. So before you paste, I'll just cut this and paste it here so that the reference will be here so that I can use it and proceed to creating the curves. I'll delete the existing coordinates. Now I'll copy and then paste it here. You can see here data is not there. So I'll right click and delete it. Here also data is not there. You can see this dash indicates y coordinate is not there. So we need not use this point. I'll delete this. And I'll put this end curve here. You can see start loft is the main command, and then start curve and end curve. Whatever is there in between, that will be converted into curve, a single curve. Now the next coordinates, this is the convex. Right click, copy, right click and paste. We are not having the coordinate here, so right click here and delete this. Similarly, here we are not having the coordinate, right click and delete. We'll copy this, copy, and you can paste it here. Again, let us go to the next coordinate, which is this. For section 2-2, copy and paste. We'll take this, copy and paste it here. Select these two and delete. We'll select this convex profile coordinates. Right click, copy, paste it here. We don't have the data for these two, so let us delete this. All the other data are available. We'll copy the start curve and end curve and paste it here. Similarly, we'll take this 3, copy this, paste it here, delete the coordinates which are not having the values. We'll copy this, start curve and end curve, and paste it here. So this is the way you have to do it for all the coordinates. All these you can copy and paste. It's not a big thing, but you have to do it very carefully. Just copy and paste. So it is very important for you to create the original file without any errors. You can see now we are in the section 5.5. We'll take the concave, copy, paste it here. We'll copy this, paste it here, and we have the last profile coordinates. Right click, copy, and we'll paste it here. Paste. There are no missing data in this, so we need not delete anything. Now when we move up, we don't require all this, so we will delete this. Only we require this end curve and loft and end. Cut it from here, and at the very last you have to paste it. Right click and paste. We have completed our coordinate file. Now we have to import this. For importing, we just need to run this macro. Let us save it first. Now in CATIA, we will open a new file. If you don't open a new file and if you have any existing file open, then when you run the macro, it will directly import the coordinates into the file which is opened. So you should be very careful about it. I'll just go to File, New, and we will open a part file. Click on OK. And OK again. So this is a part file. Now I need to go to the macro Excel file, and we will go to View. It will display the View ribbon, and here in Macros, I'll click here, click on View Macros, and from this 3 or so to say 4, I'll select this main, click on Run. It will ask, type in the kind of entities to create. 1, if you type 1, it is for points. If you type 2, it is for point and splines. And type 3, point, splines, and the loft surface will also form. All these 3 we will see. Point, spline and loft we will see in the last project. These 2 we can see it now. If I click here and type 1 and press on OK, you can see the macro is running, and it has ended. Now if we see the CATIA file, you can see all the points have been imported, and these are only the points. Suppose I will right click here and delete this. So all the imported point file have been removed. I'll go to my macro file, and again we'll go for View, Macros, View Macros. Here click on this main and run. When it asks for this, the type of entities you want to create, let us click on 2 now. So we have already seen 1 is for points, and when we click on 2 and click on OK, macro is running. It has ended. Now let us check our CATIA file. You can see points are getting found, and the points are connected by this tangential curve, which is a spline. You can see, and this is how you can import point file into CATIA. And during its import, you can create the splines. Also, you can create the surface connecting the splines. In the next video, we will start developing the section 1 aerofoil. In this video, we are going to make the aerofoil section 1.1, which is this aerofoil. So, let me hide all the 4 other aerofoils. I'll select this and hide. Now I'm left out with the section 1.1. You can see this is the section 1.1. First, let us create a plane, and we will move into the sketcher. so that we can create that section in Sketcher. So for that, I'll create a plane. For creating a plane, we will use these reference elements. We'll click here, plane, and we will go for mean through points. Let us select 3 points. Let me take this point, and again we'll go for this point. Click on OK. We have generated a plane. Now let us go for positioned sketch. Select on this plane, and you can see we want the horizontal here and vertical in this direction. So I can go for reverse V. This is the orientation that I want. Click on OK. You can see. Now I'll go for creating another spline here. You might be thinking why we want to create another set of splines. We are already having a set that we have imported directly. But why we are going for creating another set of splines? Because we need to be in more control of the spline. If tomorrow the designer changes a coordinate, or maybe if we want to do some changes, we cannot do to this unparametric curve. We have to link it with the parameters. So it may be a bit tiresome for you, but you have to create the curve so that you can be in better control of your model. Now let me take spline. You can see I'll click spline, which is here, and I'll create a spline. No need to create accurately because we are going to give the constraints. Just ensure that it should have the same number of points that here already it has been created. So I'll click here, here. So above each point I'll take a point and create a spline. You can see it has to be a rough spline. Need not create an exact spline. Now we have completed the convex side. Press on the escape key. Again we'll go for spline and one point here, here, here. You just have to ensure that the number of points are same. You can see. Sometimes you may have auto constraints. You have to delete those. Now let us give the constraints to this. We'll select these 2 points and we'll go to geometrical constraints, give coincide. Then we'll select these 2 points, geometrical constraints, coincide. You can see this is the way we will do it. Coincide. You can see. This may seem to be hectic, but you have to do it. So that suppose I have constrained this, and tomorrow what I want is, as this point is creating a problem, may not be a part of the aerofoil section, then we can easily delete this point. I'll just select this constraints, delete this, and if I want, I will select this point, right click and delete. You can see the point has been deleted. So to be in control, you have to create these splines and constrain them. I'll use Ctrl Z to get back our point and the constraint. Now the similar thing I have to do for all the points. You can see. Even for this concave portion also we will do the same thing. Select these 2 points, coincide. So we are going to do this for each and every point. You can do this by yourself. I'll do this very fast. We'll see the constrained sketch. Before you move further, let us save this file. I'll go to File, Save As, and in this exercise folder, I'll save this as Project 1. Click on Save. Now, the same thing I'll do. I'll select this, coincide, select this and coincide. You can do that for all the set of points. You can see here, I have completely constrained these two curves by just coinciding the points. Now after we do this, we have to create the leading and trailing edge. Those will be defined by two arcs. If we move over to the drawing, you can see here this RLE and RTE are the leading edge radius and the trailing edge radius. So this is defined by an arc. Now let us create these two arcs. I'll take circle directly. Let me create a circle. Now I'll take this circle, use the control and select this. And we will go for tangency. Again, select the circle and select this spline. We'll go for tangency. Now we are left out only with the radius or diameter that is given in this drawing. You can see this entire table we have fed it onto the Excel. So let us open the Excel file. In this section 1.1, if you move down, we can see the leading edge radius and the trailing edge radius. Leading edge radius is 0.75 and trailing edge radius is 0.25. Let us give these values. So this radius is, when I click here, double click, here the radius is given. The radius is 0.75. Press on the enter key. You can see the circle is made. Now we'll move over to the trailing edge. Create a circle here. Select the circle and select this spline. We'll go for tangency. Similarly, again circle will select and we'll select this curve. We'll go for tangency. Now we just have to give the diameter or radius, which is 0.25. Enter. Now let us go for trimming. We'll select this quick trim. Trim this. Just double click on quick trim so that we can trim this curve and trim this curve. You can see completely smooth curve has been generated containing the trailing edge. These things you can do only with constrained geometry. You can see I'll trim this and trim this extra portion. You can see. Similarly, here also there is extra portion. You can see here. A perfectly closed curve has been generated for the aerofoil. This curve we are going to use for the solid. So we have completed the section 1 aerofoil. Let us bring back all the others. I'll select all the point data and hide it in this visible space. Then again click this swap visible space. You can see this first aerofoil we have completed. The similar thing we are going to do for all the other sections. In the next video we are going to make the section 2 too. In the last video we have created section 1, and in this video we are going to create section 2. This is the section 1 that we have created in the last video, and this is section 2. So let us blank all the other sections. I'll select this section and hide it. I'll select all these sections and hide it, and we are left out with only section 2. Now I'll take a plane. You can click plane here and you can select mean through points. Let us select maybe this point, and this point. Click on OK. We have created the plane. Now we'll take position sketch. Select this plane. We want this vertical above, so I'll select this, reverse V. In this orientation I want my coordinate system. When I click on OK, you can see. Now as we have done before, we will select spline and we will create the spline something like this. The number of points should be same. You can see. We'll create the concave. When we are creating points for the spline here, automatic constraints are getting created. This is a coincide constraint and these two are also coincide constraint. So we have to remove those. You can see we have created the spline. The first work we have to do is remove this auto constraints. Remove this, and this constraint. Now as we have done before, we will select these 2 points. Go to constraints, coincide. Again these 2 points, constraints, coincide. These 2 points, geometrical constraints, coincide. And in this way you have to coincide all the points. These points, all these points you have to coincide. So you can see I have completed giving all the coincident constraint to the points. So this is how our curve will look. Now we will go for the leading and trailing circles. Select on this circle. We'll select this circle and select this spline. Go for tangency. Similarly, this circle and this spline, tangency, and we require to give the radius. So we'll move over to our Excel sheet. You can see this is the section 2 data, and leading radius is 0.75, trailing radius is 0.25. In fact, all the leading radius are 0.75 and all the trailing radius are 0.25. So we will go for 0.75. I'll take dimensions and here I'll go for 0.75. Double click on quick trim, trim this. I'll trim this extra portion and again this extra portion. You can see our leading edge is completed. Similarly, I'll go for the trailing side. First, let us create a circle. Now, select this circle and select this spline by pressing the Ctrl key. We'll take tangency, again this circle and this spline, and we will take tangency. Next, let us go for the radius. This is 0.25. Enter. Now, let us take the quick trim, double click on it, quick trim this, and this portion. And you can see there is a difference between this spline and the automatic generated spline. It doesn't matter because it is just a graphics issue. Both these curves are same. Now we'll finish this and we have completed our section 2. Let's bring back all the other hidden sections so that we can visualize. I'll click on the swap visible space, select all the sections and hide it here to get it in the visible space. You can see these two cross sections we have completed. So in the next video we are going to go for section 3, which is this. Let us save the file. In this video we are going for section 3. We will create the section 3. Let us hide these two sections and also we'll hide these two sections so that we are only left out with section 3. Now as before, we are just going to create a plane. Click on this plane and we'll select mean through points. Select maybe this point and this point to create a plane. Click on OK. Now we'll go for position sketch. Select this plane. Here we want this vertical above, so I'll just go for reverse V. Click on OK. Now as usual we will be going for creating the splines. Click on the spline tool and we will create spline. Just ensure that number of points should be equal. We have created the convex. Press on the escape key to exit from the command. Then again I'll take spline. We are just creating a point above the already existing point. Press the escape key. The first thing we have to do is remove this auto constraints. Coincide constraint, delete. Again, there is a coincide constraint here. Delete this. Now we have to go for selecting these two, giving coincide. Again, selecting these two, giving coincide. The same thing we are going to do for all the points. You can see all the points I have coincided. So the geometry is completely constrained. Now we'll go for the leading and trailing circles. double click on circle so that I can create a circle here, and at the same time I'll create a circle here. You can see. Now we'll go for tangency, select this circle and select this spline by using the control button for multiple selection. Again circle, spline, we'll go for tangency. Similarly here, we'll select the circle, select the spline, and we will go for tangency, circle, spline, tangency. Now let us give the dimensions. Already we have seen that the leading and trailing radius, this is the leading radius and this is the trailing radius. For all the sections it is 0.75 and 0.25. So let us give that. I'll take dimensional constraints. Select this circle. This is 0.75. Enter. And then we'll move over to the other side. For this, we will give the dimension as 0.25. 0.25. Now simply I have to take quick trim, double click on quick trim, select this and this to remove it, and this portion. You can see it is completely smooth. Now let's move over to this side and we will trim this and this, and of course trim this. You can see we have formed a completely constrained geometry and it is also closed. So we will use this profile for creating the solid. With this we have completed the section 3. We'll just finish the sketch. You can see. And then we will save this. Let us bring back all the other profiles. Select this. We'll bring back this profile and this profile. Hide it here. You can see we have completed the third section. Now we will move on to the fourth section in the next video. In the previous lectures, we have created these 3 sections. In this video, we are going to create this 4th section. Let us hide all the other sections. We'll select all this and hide. Select this and hide. Now we are left out with only the 4th section. Now, as usual, we will create a plane. We'll take reference elements, click here, and mean through points. We'll select maybe this point, and this point to create a plane. We'll take positioned sketch, select the plane. We want this vertical towards up, so we will reverse this. Click on OK. Now let us create the spline. Click on spline tool here and just create the points so that those will be connected through a smooth spline. Remember to create equal number of points so that you won't have any problem coinciding them. You can see we have completed the points and the 2 splines. The first job we have to do is we have to remove these coincide constraints so that they won't interfere when we are giving coincide constraints to the 2 points. We have deleted this. Now we have to select these 2 points, give coincide, click on OK. These 2 points, click coincide, and in this way we have to coincide all the points. You can see I have completed constraining all the points. You can do it by yourself, and then we will go for creating the leading and trailing circles. We'll create a circle here, and we will create a circle here. Now use the Control key, select this circle and spline. We'll go for tangency. Similarly, circle and this spline, tangency, and then we will go for giving the dimension. This dimension is 0.25, 0.25. Now let us trim. Double click on quick trim, trim this, this and this. And we have completed the trailing edge. Let us move over to the leading edge. We have the circle already made. Now let us go for tangency. Select this and this spline. We'll go for tangency. Let us give the radius first, because here the gap seems to be more, so we cannot form a circle which is of lower dimension. Let us see. 0.75. Press on the enter key. You can see it won't form here. If you want, you can also create a tangency now and see. You can see there is problem. Everything is red. So I'll go for Ctrl Z to undo the tangency constraint. Now let me take a line. We'll take this point and create a line something like this. We'll take this line again and the spline and give a tangency relation between them. Now I'll take this circle and I'll take this line, give a tangency. Now I'll take quick trim, double click on quick trim, trim this line, this curve and spline extra portion. Press on the escape key and delete this line, as the position of this arc is actually perfect tangent to the line. So I'll click on this point and I'll fix this point at that position. Click on OK. I'll delete this coincide constraint. You can see I've selected the coincide constraint and delete it. Now when you move this, it is free. So I'll just select this point and I will use Control button for multiple selection and select this point. So point to point, we will go for coinciding. And you can see the sketch is fully constrained and it is completely closed. Exit workbench. And we have completed the fourth cross section. Let us bring back all the other cross sections. I'll select all and hide it here. Swap visible space. You can see these 4 sections we have formed. In the next video, we are going to create this 5th section. In this lecture, we are going to complete section 5. We have already completed section 1, 2, 3, 4. Let us hide these 4 sections so that we can focus on section 5. Let us create a plane. Click on this plane, mean through points, this point, and this point. Click on OK. Now we'll take position sketch, select this plane and we'll reverse this V. Click on OK. Let us form the spline. The number of points should be same. Again we'll take spline, create a spline on the concave side. You can see we have completed the splines. Now we will go for coinciding. We'll select these two and we'll coincide. Select these two, coincide. This way we have to coincide all the points. You can see all the points I have coincided and I have attained a completely constrained spline. You can do it by yourself, and then let us create the leading and trailing circles. I'll double click on circle, create a circle here and create another circle here. Now we'll take this circle and this spline, go for tangency. This circle and this spline, go for tangency. Now we'll give the dimension. This is 0.25. Radius. Now double click on quick trim. Trim this curve, and this curve. You can see. Now let us move over to the other side, which is the leading side. And here also we'll take this circle and this spline and give a tangency relation between them. We'll take this circle and this spline and give tangency relation. Now let us go for trimming. Oh, before that we have to give the dimension. We'll take this radius and we'll give 0.75. Double click on quick trim and trim this portion, and this extra portion. You can see. With this we have completed the section 5. Now exit this. Let us save this file and we will go for creating the main body of the blade. Let us bring back all the sections. All these sections, hide it in this invisible space and then swap visual space. You can see these are the 5 sections that we have made. Let us hide this again and bring back only our sections which are required for the solid. We'll swap the visual space. When we zoom, we'll catch hold of this section and hide it here. If you swap the visual space, you can see this is actually the section which will contribute for creating the solid. Let us do the similar thing for all the other sections. We'll select this section and hide it here. Select this section, hide it here. Select this section, hide it here. And we'll select this section. We'll hide it here. And when you swap the visual space, you can see all the sections we have got in our visual space. Let us create a solid from all these sections. We'll go to Insert, Sketch Base Features, Multi-Section Solid, and let us select the cross sections. We'll select this cross section, this cross section, this, and this cross section. You can see all the cross sections have been selected. You have to ensure two things while making this multi-section solid. First is the direction. The direction should be clockwise or anti-clockwise. That is, all the sections should have the directions as clockwise or anti-clockwise. You cannot have mixed directions in these 5 cross sections. Here this is clockwise, here also it is clockwise, 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 clockwise. So the direction is okay, there is no problem. But we have the second requirement, which is the closing point. The closing point should be almost in the same arc length. Here you can see the closing point is somewhere in this point, and here the closing point is here. So when this solid will form, it will form a cusp or a twisted body, which is not our requirement. Our requirement is a completely smooth body. So for doing that, we will convert this closing point into this closing point or vice versa. Here you can see these 3 have the same closing points. Only these 2 have different closing point. So let us delete this, and we will also delete this. Now right click on this and go for create closing point. You can see we can create a closing point here. Click on this and click on OK. So this is a closing point which is very similar to this, this and this. Similarly here also, right click, create closing point. We'll select a closing point here. Click on OK. You can see we have generated the closing points and all are in the same orientation. Just click on OK to see the solid. You can see this is a beautiful solid that we have created by using multi-section solids. This contains all the 5 cross sections. We'll go for the isometric view. In the next video, we will go for creating the root, which is an axial dovetail root. Till now we have completed this body, which is the main body consisting of all the aerofoils. Now we are going to connect this body with the axial root. Let us see the drawing. Here all these cross sections we have generated and we have connected them through this body. Now we are going to create this axial root. This is a dovetail structure and these are all the dimensions that are contributing towards the dovetail structure. We are going to generate this sketch and we are going to use pad to make the solid body. We need to first understand where this sketch has come, because this is a cross section and we have to see where this cross section has been generated. This is detail C. So this has been generated from this view. You can see this view C, and this is the section AA. If you see this front view, this is the section AA. So by cutting this blade along this section and viewing in this direction, this view has been generated. Now if you see, as this is the section where this cross section is coming, now we have to see this view. Here this is the axis of symmetry of the root, and this is the vertical axis. These axes are same as the axis of the aerofoil. So we have to take this plane and create this cross section. Now let us see it in 3D. You can see here this is the leading edge and this is the trailing edge, and this is the section. So we are going to form this section. When you see from this side, it is this view. We are going to take position sketch and create sketch on this plane. You can see this is the plane, and we are going to create it in this orientation. You can see when you click on OK, this is the orientation in which you have to create the dovetail root cross section. Here at the back side of this view, it is the trailing edge, which is this edge. Even here, if you see, back side we have the trailing edge. You can see this is the leading edge and back side is the trailing edge. So this is the view. Now let us start by building a rough profile. You can see this is the section that we are going to generate. Let us create this rough profile. We'll take profile, click here, and here you can see we are creating a dovetail root. Prevent this auto constraints, click here, and we will click somewhere here. Click on escape. We'll create this half profile and then we will mirror it. Let us see. Let us give the geometrical constraints first. I'll select this line and use the control button for multiple selection. Use this axis. Between these two, I will use coincidence. Now when we see the drawing, you can see here, this angle is 56 degrees. Let us give that. From this line to this line, this angle is 56 degrees. Next, this is 101 degrees, which is the included angle. This is 101. Now, there is a dimension here 18.9, which is from this lobe to this lobe. If you generate a R1 radius here, from this lobe to this lobe, the dimension is 18.9. Let us give that. First, let us create the lobe. We'll take fillet and we'll select these two. Now, we'll double click this and give a value of 1. We have created this R1 radius, that is a fillet. Now we are going to give 18.9. So in this case we are going to take this axis and this arc, and here we are going to give 18.9 divided by 2. You can see. Next, we have to give this dimension, which is very important. You can see from the base at a distance of 5.9, the root width is 14.8. This dimension we are going to give. We can give that by using a point. We'll take point and click here to create a point somewhere on this line. Now we'll take dimensioning from this point to this base. We'll take this value as 5.9. You can see here. We'll give this value 5.9. And from this point to this axis, this value we have been given as 14.8. 14.8 divided by 2. You can see. Now as you move up, this is 4.9. From here to this vertical axis, this is 4.9. Now we'll take a line from here, we'll connect it up to here. Now this height of this blade root is given somewhere here. You can see this is 15.4, which is the height of this blade root. So we will give the dimension here. From this top and to bottom, this is 15.4. You can see the sketch is fully constrained. Now let us select all these curves. We'll select this curve, this curve, this curve, this and this. And we'll move over to Insert, Operation, Transformations, Mirror. About this axis. You can see the other half has been created and it is completely constrained. Now that we have created the sketch, let us exit workbench. You can see. Now let us go for pad. We'll use pad. Click on pad. Select this sketch. This says we have some elements in the sketch we have not converted into construction elements. So let us go to the sketch again. I'll click here to go into the sketch. Here it is saying about this point. We'll select this point. You can see I've selected this point and I'm going to convert it into reference. If you select this, it will convert this into a construction element. Click. You can see it is a construction element now. Exit workbench. When you click OK, you can see the solid has formed. Now double click this. Let us give the dimension properly. Here, if you see this, at 39 mm, at 25 degrees, these two cuts will be made. So, we can keep this as long as we want. Length of this can be as long as we can keep. We'll click here and this length we can increase. Anyway, we are going to cut it. So let me keep up to this length. Click on OK. You can see. We have formed the axial root. But the length has not been given yet. You can see this is the length. So for that, let us create a sketch again. We'll take position sketch, select this plane. You can see this is leading and this is trailing, and the view has to be exact so that you won't get confused. This is your leading and this is your trailing. This is V and H, so our orientation will be perfect. When I click on OK, you can see this is leading and this is trailing. Here also this is leading and trailing. Now the dimensions will not be confusing. I'll take a line, connect to this origin and click here. And I'll take dimension between this line and this axis. This value is 25. Let us give 25 and I'll convert this into reference. I'll convert this into reference. Now let me create the section. This construction element is on, so we are creating this construction elements. I'll click this off. Connect this. Again, I'll create another profile here. And I'll connect here. Now I'll take this line and this line. We'll take parallelism. Again this line and this line. We'll take parallelism again. Now let us give the distances. From this line it is 21.5. From this line to this line, this is 21.5. And again, I'll take distance between this line and this line. This is 39. You can see these free dimensions are not of our requirement because we just need to cut it. So this line and this line should be constrained. We'll finish the sketch. Now by using this pocket, we'll move in the opposite direction, and here we can go for up to last. Click on OK, and you can see our axial dovetail route has been formed. In the next video, we are going to give the finishing touches to the model. In this lecture, we are going to give finishing touches to the model. Finishing touches like the blade height we are going to maintain and the corner radius we are going to give. Any chamfer or radius we are going to give in this stage. Here, if you see closely, as we are going to select the edge blend or edge fillet, then we require the edge to be perfect. Here you can see there is an edge here which is not required. This has been formed due to the way we have made our sketch. So we have to change this and we have to eliminate this edge. I'll double click on this solid which we have created by using pad from this sketch that we had made, and we will click on this icon. You can see now we are inside the sketch which we have previously created. I'll select this and make it reference. You can see it has converted to reference. Again I'll select this, convert it to reference. So both these lines I have converted to reference. It is because of these two lines that there is an edge at this point. So I'm going to create a single line here. From here you can see I'm forming reference elements. So I will click this to switch it off so that it will be a solid line. Now I'll connect it to this endpoint. Now when I go outside of this Sketcher workbench and click on OK, you can see the edge has been removed. I did all this exercise to just tell you that how important is the edge. Now if I go for edge fillet, I'll go to dress up features, edge fillet, and select this edge. You can see. Now I'll take 3 mm and you can see here. If you see the drawing, the transition between the profile, body and the root is given as 3 mm all around. You can see here 3 mm all around. So we have given a fillet of 3 mm. You have to find out in the drawing where all the other radius have been given. There is no other radius that we have to specify. So we have completed all the fillets. Now we are left out with this blade height, which is 90. We have created up to section 55, which is 95. So we have to create up to 90. Let us do that. Let us create a plane. I'll click on this reference elements on plane and I will select here offset from plane. Select this plane and I'll give a value of 90, which is our blade height. Press on the enter key. You have created a plane. Now let's go to insert, surface based features, split. Now we are going to split this body about this plane. When you click on OK, you can see the upper portion is remaining, so it's not correct. We will double click on this split and here we will choose this arrow downwards. Just select it to move the arrow. We want this lower section. Click on OK and you can see we have given the blade height. Let us hide this plane and our blade model is finished. So with this we have completed the project 1, which is the 5th stage compressor rotor blade of an aero engine. In the next section we will proceed to project 2, which will contain a very important root, which is a radial root. We will see that in the project 2.